Zoom notes for AP Calculus on the topic of basic differentiation shortcuts. Okay. So remember, differentiation refers to the process of finding the derivative. Previously, we looked at how you find the derivative using the formal definition with limits, but in practice, there's some shortcuts you can use that can save you a lot of time. So the first shortcut we're going to look at is the constant rule. So if C is a constant, not changing, like 5, the derivative of any constant just by itself is 0. If you think about that, when you have a constant, let's say you have a function like y equals 3, well, that's just a horizontal line, right? Remember, the derivative gives you the slope, so the slope of any horizontal line is just 0. That's how that one works. Then, the rule when you have just a basic x to raise to some constant exponent, what you do is it's called the power rule. So x raised to a power. You just bring the exponent out in front, and here, and then subtract 1 from the exponent. So you reduce the exponent by 1. The constant multiple rule says if you have a constant out in front of a function, when you take the derivative, that constant just remains as the coefficient out in front. And finally, the sum and difference rules tell us that if we have more than one function added and subtracted, we can take the derivative of each one separately. Well, one thing I forgot to point out here, this notation here, whenever you see the d over dx, something in brackets or parentheses, you see that? What that means is take the derivative of whatever's inside the brackets or parentheses. And here, that over dx tells us it's with respect to x. So x is their parameter. So let's take a look at some examples and see how these shortcuts can make the process of finding the derivative much more efficient and not take nearly as long. So it says find the derivative of the function. Okay, so we've got f of x, so the notation for the derivative would be f prime of x. And notice we've got a bunch of different terms added and subtracted. In this case, they're all added. So that's where the sum and difference rules comes in. It tells us we can derive each one separately. So the derivative of x to the 4th, using the power rule here, says we bring the exponent out in front as a coefficient. So bring down the exponent 4, and then you reduce the exponent by 1. So now 4 minus 1 gives you 3. So that's the derivative of x to the 4th. Plus, again, we're taking the derivative of each of these separately, the derivative of x cubed, you bring down an exponent of 3, and you reduce the exponent by 1. That's x squared. And then derivative of x squared, you bring down the 2, and now the exponent is just a 1, so you don't even need to write it there. And on the x, notice the exponent on the x, even though it's not written as a 1. So you bring down the 1, and then you'd have x to the 0. But anything to the 0 power is just 1, so you don't even need to write that. The reason why I see the point that would be 1 also is because if you just look at this part of the equation, if we did have the first 3 terms, then you can see that it would just be linear. The slope would just be a factor 1, which is what we got there. And find the derivative of 7. So I'll just write it here. It would be 1 and x is 0. Derivative of 7, derivative of any constant by itself is 2. And again, another way to see why that would be 0, if you think about the transformations, this plus 7, all that does to the graph is shift the graph up 7 units. But notice it doesn't change the shape of the graph at all. So it won't affect the slopes at all. Hence, the derivative of that part is 0. The derivative gives you the slope. So then if we just simplify that a little bit, 4x cubed plus 3x squared plus 2x plus 1 would be f prime of x, your derivative. That would give you the slope of the function or rate of change of the function for any x value you substitute. Okay, let's look at the next example now. On this one, it's written as y equals, so we use the other notation for the derivative. dy over dx. And notice here we've got some coefficients already in front. But remember, the constant multiple rule says those coefficients just stay out in front when you take the derivative. So the 2 stays out in front, but when you use the power rule on the x cubed, that 3 gets multiplied by the 2 out in front. So 3 times 2 gives you 6, and then you reduce the exponent by 1, so it becomes x squared. Same thing here. Again, since they're added and subtracted, the sum and difference rule tells us we can take the derivative of each one separately. So you bring down the 2 times -4, it's -8. Now it's x to the first. Derivative of 3x, bring down the 1 times 3 would just be 3. And that's x to the 0, so you don't need that. You saw over here. X to the 0 is just 1, and the derivative of -5 is just 0, so you don't need that either. So that would be your derivative. Alright, let's take a look at some more complicated examples now. So, the power rule still works with the radical and fractional exponents. It just looks a little more complicated. So, it's easier to use the power rule though if you put everything in exponent form. So, anytime you have a radical, that's x to the first, that's the square root. So, square root of x to the first, that's the same as x to the 1/2. Plus, we get x to the 2/3 plus x to the -3/4. So, using the power rule on this, the derivative, again, since they're added, you can take the derivative of each one separately. So you bring down the 1/2 out in front, and when you subtract 1 from that, that's like subtracting 2 over 2. So now you'd have x to the 1/2 minus 2/2 is -1. And then you bring down the 2/3 out in front, so plus 2/3. X, again, you subtract 1, which is like subtracting 3 over 3. So the x to the -1/3, 2/3 minus 1/3. And then bring down the -3/4, so you can -3/4. X, when you subtract 1 from that, that's like subtracting 4/4, to give you -7/4. But in our final answer, we don't want to leave any fractional or negative exponents, so let's go ahead and simplify our final answer here. So the derivative, f prime of x. Well, since it's a negative exponent, we move it to the denominator, so the 2 is already on the denominator, notice. And x to the 1/2 is the same as the square root of x. On this one, the 2 is on the numerator, the 3 is on the denominator already. Again, the negative exponent moves that to the denominator, and x to the 1/3 is the same as the cube root of x. Putting it back in radical form. And then minus, 3 is already on the numerator, 4 is already on the denominator. Again, a negative exponent means it moves to the denominator. Become x to the 7/4, and putting that in radical form would be the 4th root of x. And here you can either put the 7 on the inside, or typically it's easier to actually put it on the outside of the radical. So when you're evaluating things, this radical form would be easier. But notice, rational exponents or fractional exponents are easier to use when you're taking the derivative because it's easier to implement the power rule. So they both have different uses. All right, let's take a look at the next one. On the next one, before we take the derivative, we actually want to rewrite the function. Because all of x's there are on the denominator, so this is like x to the first. When you move it up to the numerator, that makes the exponent negative. So 1 over x to the first is the same as x to the -1. Minus, here we've got 2, same thing, move the x squared up to the numerator, makes it x to the -2. Plus, this is x to the 1/3, move it up to the numerator, becomes x to the -1/3. Minus 3, this is x to the 3/4, move it up to the numerator, becomes x to the -4. But notice this is not the derivative yet. This is still just the original function, y. Then we're going to implement the power rule on each one of these. Now they're just added and subtracted. And now we have the exponents on it. So the derivative here would be dy dx. So the equation is y equals. So again, using the power rule, you bring down the -1. X, subtract 1 from that would give you -2. -2 times the -2 that's already out there will give you a +4. X to the subtract 1 from the -1 is 3. -1/3. X to the Negative 1/3 minus 1 plus minus 3/3 gives you negative 4/3. And then negative 3/4 times negative 3 is a positive 9/4. X to the subtract 1 from that gives you negative 7/4. And same thing in our final simplified answer. We don't want to leave any fractional or negative exponents. So let's simplify it. So if you bring that x, the negative to the denominator, we'd have negative 1 over x squared. You can leave the negative on the numerator or denominator or out for all the same. Plus 4 over, move that to the numerator, is x cubed, negative positive exponent. Minus 1 over, we've already got the 3 on the denominator. And in radical form, when you move that down there, that'd be the cube root of x to the 4th. Plus 9 over 4. When you move that to the denominator, it'd be the 4th root of x. So that would be your simplified derivative. Now the next one, notice, this whole thing is divided by 3x cubed. So in this form, based on the rules we know right now, you can't take the derivative. Because you can only take the derivative separately if they're added or subtracted. But what we can do is split up our fraction. When you have a single denominator like this, that really means you can divide all of these by the 3x cubed, by that denominator. So let's go ahead and write it that way. Divide it all by 3x cubed. And now we can simplify each one of these again before we take the derivative. So again, be careful with your notation here. This is still g of x, the original function. So the 2/3 doesn't reduce it. So we can leave that as a constant out front. And then here 3 of the x's cancel, so you have x to the 3rd, subtracting the next one. Minus 6 divided by 3 is 2. Here the x cubed divided by x cubed is just 1. Reduce that. Here the 3 divided by 3 is just 1. And then we'd have x to the negative 1. X left over on the denominator. Minus 4/3. Here we'd have x squared left on the denominator. Move it up, makes it x to the negative 2. And 9 divided by 3 is 3, and x is the denominator, so move it up, okay, x to the negative 3. So here we're utilizing negative exponents again, so we can use the power rule. So again, this is still just g of x. Now, let's take our derivative. G prime. So 3 times 2/3, well, the 3's are going to cancel, leaving you just 2. X to the 2nd. The derivative of a constant by itself, negative 2, is just 0. We don't need that at all. Derivative of x to the negative 1 would be negative x to the negative 2. Negative 2 times negative 4/3 is positive 8/3. And x to the negative 3. And negative 3 times 3 is negative 9. X to the negative 4. And again, we don't want to leave our final answer with negative exponents. So let's go ahead and simplify it as our last step. This first term is already simplified, 2x squared. Minus x to the negative 2 is the same as 1 over x squared. Plus 8 over 3, move that to the number, becomes x cubed on the number. Minus 9 over x. So that would be your simplified derivative with no negative exponent. Now let's take a look at one where it's kind of a general notation. It says find an expression for h prime of x. In other words, the derivative of h. So h prime of x. So we're just writing in general form. We don't know specifically what f of x and g of x are, but notice we're just adding and subtracting. So again, we can apply that rule for the sum and difference. You can take the derivative of each of them separately. So, and the constant just stays out in front. Remember, when we took the derivative, the constant just stays there, so the derivative 2 would just stay there. And when you take the derivative of f of x, well, the way that's written is f prime of x. Minus the derivative of g of x, you would just write that g prime of x. And then the derivative of negative 2x cubed would be negative 6x squared. So the power rule. The derivative of 7x would just be plus 7. 1 times 7 is 7. X, you just have x to 0, the derivative of negative 4 is 0. And that's really all you do. So this is kind of leading us to problems later on where we'll have some more information about which f or g. get used to working in this general notation when you don't know specifically what the functions are. Now, it says, using the given input function, find the following. So what we're trying to find is f prime of 64. Well, all that means is we want the derivative or slope right at 64. So before we can plug in 64, we actually have to find the derivative. So let's go ahead and rewrite this because we've got a radical there. So that'd be x to the 1/2 minus x to the 2/3. Then we can take the derivative. F prime of x would be 1/2 x to the negative 1/2 minus 2/3 x to the negative 1/3. And before we plug in the 64, let's go ahead and simplify that. It'll be a lot easier. So it's 1 over 2 times the square root of x minus 2 over 3 times the cube root of x. So that's the derivative or slope for any x value. But we want it specifically for 64. So now we can just plug in 64 to f prime of 64. 1 over 2 times the square root of 64 minus 2 times 2 over 3 times the cube root of 64. Just simplify it from there. F prime of 64. Well, the square root of 64 is 8 times 2, so that would be 1/16 minus cube root of 64 is 4. 3 times 4, we can reduce that to 1/6. 1/16 minus 1/6. Just get a common denominator for those. It'd be 48. So that's the same as 3/48 minus multiplied by 8. 8 over 48. So we get the derivative or slope specifically at x is 64 is negative 5/48. Now let's take a look at finding the equation of the tangent line and normal line, the graph of the function of the indicated x value, in this case x equals 2. So let's just draw a little picture of what this looks like so you can see what we're actually finding. Let's say this is our function at x. Well, the tangent line, let's say this is our point of tangency. The tangent line all would look like that. That's the tangent line. Has the same slope as the function at that point. And what the normal line is, it still goes to the point of tangency, but it's actually perpendicular to the tangent line. So the normal line is something like that. Where those are at a right angle. So remember, there's two things we need for the tangent line: the point of tangency and the slope. So let's find the point of tangency first. Sorry, by just substituting in 2 for x. That gives you 4 minus 1, 3 squared, which is 9. So now we know that x is 2, y is 9. There's our point of tangency. And then, in order to take the derivative, you'd actually need to multiply that out. So 2x minus 1 times another 2x minus 1. This is still y, would be 4x squared minus 2x minus 2x is minus 4x plus 1. Now it's easy to take the derivative just using power rule on each term. So the derivative is 8x minus 1. That's the derivative for any x value, but we want it specifically in our point of tangency. So the way you write that, you want the derivative specifically when you're plugging in x equals 2. So it'll be 8 times 2 minus 4. 16 minus 4 is 12. So there's the slope of tangent. So now using point slope form, we can say the tangent line y minus the y coordinate 9 equals the slope is 12 times x minus the x coordinate of 2. And for the normal line, it goes to the same point of tangency, so that part will be the same. So it'll be y minus 9. But in order to be perpendicular, remember perpendicular lines have slopes that are opposite reciprocals. So the reciprocal of 12 is 1/12, and the opposite makes it a negative. So negative 1/12 would be the slope of the normal line. And again, it goes to the point of tangency, so it'll still be negative. But once you have the tangent line, it's really easy to get the normal line by just taking the opposite reciprocal of the slope and make it perpendicular. Finally, let's take a look at determining the points, if any, at which the function has a horizontal tangent line. So what this means, a horizontal tangent line is this f of x. And here's your point of tangency. Just like that. That's the horizontal tangent line. Okay. So the tangent line, one thing you know for sure, the slope is 0. Remember the calculus word for slope is the derivative. So here we would just want to set the derivative equal to 0. So let's find the derivative first, which is 6x squared plus 6x, and then set it equal to 0. Factor out the 6x, you're left with x plus 1. So you get x equals 0 and x equals negative 1. And it says the point, so that means you need both coordinates. So if you plug in 0, get negative 1. So one of the points we have is 0, negative 1. And if we plug in negative 1, oops, I put a square there accidentally. Sorry, yeah, that's right. It's cubed here. So this was supposed to be cubed. So that would be negative 2 when it's cubed. And that would be positive 3 minus 1 would give you 0. So our other point would be x was negative 1, and y is 0. So those are our 2 points where we have horizontal tangent line. Now, in this case, it looks like the coordinates are just reversed there, but that's actually just a coincidence. What this function really looks like, that's usually not going to happen, is those are the 2 points where we have horizontal tangent lines. So 0, negative 1, negative 1, 0. And this is a cubic graph, so those are our 2 places where we have a horizontal tangent line. So a rough sketch of this would look something like this. There's up there, there's a horizontal tangent line there, and there's a horizontal tangent line. It's just coincidence that the coordinates are reversed. And that concludes Dutch for AP Calculus on the topic of the basic differentiation formula.